because this is basically the same thing. It's just you're missing out on the acid-base ones. So when you do a titration, you're using a solution that has a known concentration to figure out an unknown concentration. When you do this, you add the acid or base, whatever type of titration you're doing, until it reaches what's called the equivalence point. When it reaches the equivalence point, the moles of acid and base are equivalent, which means then you can do a stoichiometry problem to figure out that concentration of your unknown. Most of the time an indicator is used for these. The couple that we've done before, like we did one first semester where the indicator was actually a redox reaction where it changed color. Phenolphthalein is the indicator that we use. It's for most acid and base reactions, and we'll talk a little more about indicators later. But it turns pink if you're titrating in the strong base and you're starting with the acid in the flask at the bottom. Then the phenolphthalein turns pink right around 8, which is usually what they use for either strong acid, strong base, or weak acid, strong base titration. So what we're going to look at today is how to do a couple different types of calculations. And again, this has been kind of pared down a little bit, so you'll see that there's some stuff in here that you won't have to know, and I'll explain that as we get to it. So here's just another little diagram of titration. Hopefully you watched that video that was in the lab yesterday. She does a really good job of explaining it. Just as a review, again, I'm most worried about people that are going on to take more chemistry because you didn't get the lab experience of doing the specific acid-base one. So she did a nice kind of overview, and you could watch her go through and do that titration just so you've at least seen it before. So most of the time they have the acid in the flask at the bottom, and the base is in the pipette or the burette at the top. The known concentration is what you're dropping in, and then you're using this known concentration and the amount of the known concentration to have this reach the equivalence point, which is when you see that real light pink color. Like we said, this is probably a little bit darker. You usually want it a little bit lighter than that. And then you do the calculation, and we'll review that calculation, and that's the calculation that you need to do for your lab. So the first type of titration you can look at is a strong acid, strong base titration. So you did one of these in the lab yesterday. You guys, let me know if you feel like I don't think there's anybody waiting in the waiting room, but if you see somebody that's trying to get in, let me know. I think everybody's in here right now, but I always worry somebody's gonna be left out there. Okay, so strong acid, strong base titration. The other thing you'll want to make sure you can do is identify the graph of a strong acid, strong base titration compared to a weak acid, strong base titration. So when you're looking at a graph from a strong and strong titration, there's a couple things you can look at. The first thing is the initial pH. So if you have strong acid, strong base titration, the initial pH is going to be very low. So it's going to be below 2. So that's your first indicator that if all you have is the graph, that this is strong acid, strong base. Because when you have this set up, your acid is in the flask or the beaker, and then your base is in the burette, and then the pH meter is recording whatever's in that flask. So if the acid is in the flask, that's going to show a very low pH, and that's because a strong acid has a low pH. The next thing that you'll see is the equivalence point. So the equivalence point of a strong and strong is always at 7. It's exactly at 7. You don't have to do any calculation for that. So in a minute, when they ask you the question of what is the pH of the equivalence point, if it's strong acid, strong base, you automatically know it's 7. You don't have to do a calculation for that. The last thing that you'll notice about the curve of the graph is that it goes over, up, over. Okay, so it's a very kind of defined graph. Goes straight over, straight up, straight over. So if you remember when we did the buffer labs before we left, this curve was a little more like this. And you'll see that in a minute when we look at the weak acid, strong base. But if it is strong and strong, you're going to see over, up, over. So anytime it asks you what are features of the graph that indicate that it's strong and strong, a strong acid, strong base titration, those are your three things. Low initial pH, equivalence point is at a 7. So you can see if you look over here, the middle of that straight line in the middle is at 7. And then the third thing is the shape of the graph, where it goes straight over, straight up, and straight over. Okay, the other type of titration that's not, we don't see this as much, and we usually don't do these in class, these are not as common, is strong base, strong acid. And the only difference here is that on these, the base is in the bottom, and then you're using acid in your burette at the top. So the acid, and so again, pH meter is in whatever's in the flask. So this one you can see has a very high pH. That would again indicate that this is strong and strong. Still the same graph shape as the other one, it's just the reverse because your pH meter is reading the base to start with instead of the acid to start with. All right, the next thing you'll have to do when you have these titrations is do calculations. So there's a couple different types of calculations you'll have to do. They're very, they follow this pattern every time. So the first thing you want to do when you're doing these is identify what type of titration it is. So is it a strong acid, strong base, or is it a weak acid, strong base? And those are the two types that we're going to focus on, just again, because we have such a short amount of time here. They might ask you what the initial pH is. So to get the initial pH, it's the pH of the strong acid solution. So if you remember, if you have the concentration of a strong acid solution, that's equal to the concentration of the H+. So then if you know the H+ concentration, then you can use your pH calculations to figure that out. Before the equivalence point, so if you want to know the pH before you've reached the equivalence point, then you're going to use something called the Bca table, and that's what we're going to learn how to do today. And you're going to use that to find the pH. And then if it's at the equivalence point, then that's an automatic pH of 7. So you don't have to do a calculation for this one. If it wants to know what is the pH at the equivalence point, then you just say that it's 7 because it's a strong acid, strong base titration. That's kind of a by definition thing. The only other thing you could have to calculate on this is either how many milliliters to reach the equivalence point, or they might ask you what is the concentration of the unknown. If they ask you those two things, you're going to use solution stoichiometry, and that's a calculation we've done before. So the solution stoichiometry is when you start with the milliliters, the molarity, and then you run it through a stoichiometry problem. We'll do an example of one of those in a second. If you want to know beyond the equivalence point, now the yellow ones you don't have to learn how to do. I'm just leaving these in here so that you've at least heard this before. If you take higher levels of chem, you're going to have to do this. But if it's beyond the equivalence point, you go back to that Bca table and then you find the pH. But we're going to focus just on these and then also on the stoichiometry. Okay, so this is what they look like. So this one says you have a 50 milliliter sample of 0.2 molar sodium hydroxide. It's titrated with 0.2 molars of nitric acid, and we want to calculate the pH. Okay, so on this one, first thing when you see these titration problems is identify what type it is. So sodium hydroxide is a strong base, nitric acid is a strong acid. Okay, so that will then tell you which of these two types of calculations you need to do. So if I want to know what is the pH after adding 30 milliliters of HNO3, we're going to use something called a Bca table. That stands for before, change, after. So it's a little bit different than an ICE table. If you remember, in ICE table, you had to use molarities. For a Bca table, it has to be in moles, because what you're doing is you're trying to figure out how the H+ and the OH- interact with each other, what gets used up, and then what you're left with. So when we're doing this, when you use this Bca table, For strong acid, strong base, the only things reacting are the OH minus from the strong base and the H plus from the strong acid. Because those other, if you remember back when we talked about salts, the sodium doesn't affect the pH, and the other ion with the nitric acid, the NO3, doesn't affect the pH. Okay, so when we set up a Bca table for strong acid, strong base, which is what we're doing here, all you need is H plus OH minus generates water. Because in that solution, when those two things are mixed together, that's what's reacting. So in the acid in the bottom, you have H plus, you're dropping in OH minus, and then that's going to combine together to make water. So what you're trying to do is figure out how much of that H plus is going to get used up, how much OH minus is left, and then that's going to determine what your pH is after you've added that together. Okay, so to fill out a Bca table, because the Bca table is in moles, you have to do some calculations before you put things into the Bca table. Okay, so to figure out the H plus, I have to look at how much nitric acid I have. So I have 30 milliliters of HNO3. So I have 30 milliliters. And this is, I'm just going to call this 30 milliliters of H plus, because I don't care about the NO3 because that's not going to affect the pH. I'm going to change this to liters, and you can do that before you put it in this little conversion if you want. And then it is 0.2 moles per liter. So what this is telling me is this is telling me how many moles of H plus are in that acid before I add the OH minus to it. Okay, so if I solve this, it's 0.01 moles. I'm sorry, wait a minute, I'm looking at the wrong here. Yeah, 0.006 moles of H plus. Okay, so that goes right here. So that's how many moles of H plus are in this beaker to start with. Then I need to know how many moles of OH minus are getting dropped in there. Oh, actually, you know what? This is flipped around here. This won't change our calculation, but just so we know here. This is actually, in this particular one, this is the OH minus and this is H plus, just so there's no confusion there. Okay, so then for the OH minus, I have 50 milliliters. Change it to liters. And then it is also 0.2 moles per liter. So that's 0.01 moles of OH minus. So then that goes here. And then for water, because water is a liquid, we're not going to worry about that. So that's going to get just ignored. Okay, so then once you look at this, the one that's present in a lower amount is the one that's going to get used up. So in this case, the H plus, there's less H plus. So that's going to be what I subtract. So the H plus is all gone. The H plus gets all used up, and there's 0.004 moles of OH minus left. Now that we know how much OH minus is left, we can use our pH calculations that we used. But before we can do that, you have to change this back to molarity. So to do that, I'm going to divide by the new volume. So I mixed 50 milliliters with 30 milliliters. So now I have 80 milliliters total. So when I calculate the molarity, remember molarity is moles over liters. So I have to take the moles that I have left divided by liters, which would be 0.08 liters of solution. So I'm going to take 0.004 divided by 0.08, and that gives me 0.05 molar OH minus. Okay, so then from there I can go back to my pH calculations, which we did a little bit before in the last couple of chapters. So I'm going to take the POH, so negative log of OH minus equals POH. So my POH is 1.30. And then to get the pH, I'm going to subtract from 17. So my pH is 12.70. Okay, so that would be my pH after I've added that much HNO3. If I wanted to know the initial concentration, or I'm sorry, the initial pH, then I would just use this 0.2 molar sodium hydroxide concentration and figure out the pH from there. Okay, the other question on this one is, what is the pH at the equivalence point? This is what we talked about a minute ago. Because it's strong acid and strong base, by definition, the pH is 7.00. And that's because it's a strong acid, strong base titration. So no calculation needed for that one because it's a strong acid, strong base. You don't have to do a calculation for it. Okay, the only other calculation you could do with this is if it asks, like I said on that previous slide, how much is needed to get to the equivalence point, or what is the concentration at the equivalence point. Anytime you see equivalence point and it doesn't ask about pH, it asks either about volume or concentration, then that tells you you'll have to use stoichiometry, and we'll do a stoichiometry example when we do the week one. Okay, take a look at this for a second. Any questions about where any of that stuff came from? Okay, so now let's look at a weak acid and a weak base. I'm sorry, weak acid, strong base. So first thing we want to look at is the graph. So if you have a weak acid and a strong base, so this is the only other type of titration we're going to worry about. There's three things that you're going to look for. Initial pH is not as low. So on that last graph, the initial pH was below 2. On a weak acid, strong base, the pH is going to be kind of between 2 and 4 usually. The second thing you're going to look at is the equivalence point. So on this one, the equivalence point is usually 8 or above. Usually it's right around 8, but it's definitely above 7. So you're not going to see it right at 7, you'll see it above. And then the third thing is you'll look at the shape of the graph. So notice on this one, it's more of a gradual curve. So this is going to look more like the graph that you generated from your buffer. So when you look at this, if this was strong, this would go straight across, straight up, and straight over. So the difference here is that there's more of a gradual curve going up. And that is your characteristic shape for your weak acid, strong base. Calculations for this one are a little bit more involved than the strong and strong. The first one is the initial pH. So to figure out the initial pH, you can't assume that the concentration of the acid is equal to the concentration of the H+, because if you remember, a weak acid doesn't completely dissociate. So to find the initial pH, you have to do an ice table using the Ka. So that's going to be a little bit of review of what we've done before. If you want the pH between the initial and the equivalence point, like after you've added a certain amount of acid, like we did in that last one, we're going to go back and use that Henderson-Hasselbach equation, just like adding base to a buffer. And then halfway to the equivalence point, the pH equals the pKa. And pKa, again, is the negative log of the Ka. So we'll do a practice one with that. So these are the three that we're going to focus on here. And then same as the other one, if you want to know the concentration or the volume to get to equivalence point, that's going to be solution stoichiometry as well. These down here, we're not going to do, but just so you know, at the equivalence point, you would use an ice table by using Kb of the conjugate base. If it's beyond that, then you would have to look at moles of weak acid, moles of OH divided by total volume. Again, we don't have time to do that. So those are there in case you want to refer back to this at some point in the future. We're just going to focus on those first three and then the solution stoichiometry. Okay, so let's look at an example of this one. So this one says we have a 40 milliliter sample of HNO2, which is a weak acid, and it's titrated with 0.2 molar KOH, which is a strong base. Okay, so this one is actually the way I do the other one to begin with. So this one, the weak acid is in the bottom, and then the strong base is what is getting added. So the first question is, what is the volume required to reach the equivalence point? So if it's not asking about pH, so like I said on that previous slide, if they want to know concentration or they want to know volume, this one we're going to do solution. You're going to start with the information, or you're going to start with the one that has more information. So the weak acid has a milliliters and a molarity with it. So we're going to use that to start with. So I'm going to start with my 40 milliliters of HNO2, convert it to liters, and then use the concentration to get it to moles. Then I have to know the ratio between the two. So this one you can see is 1 to 1. So HNO2 plus KOH gives you H2O plus KNO2. So this would be 1 mole KOH for every 1 mole of HNO2. Then I want to know what is my volume. So I have a concentration of KOH, so 0.2 moles of KOH per 1 liter would give me 0.02 liters of KOH, which you could then, if you want, change to milliliters, because usually when you're doing these titrations, you're measuring in milliliters. So you don't have to change it, but you can. That sometimes will make a little more sense. So 20 milliliters of KOH is required to reach the equivalence point. The other thing on this one, since this is 1 to 1, we've talked about this before and how I don't necessarily recommend it, but you could use M1V1 equals M2V2 if it's a 1 to 1 ratio. So if you don't like the solution stoichiometry and you would rather do it that way, you can. You just have to be careful, because if it's not a 1 to 1 ratio, you have to adjust that accordingly, and sometimes that doesn't always work out. The safer way to do it if it's not 1 to 1 is to do the stoichiometry like we've done before. Okay, questions on that one? Next one, now it says we have same thing, HNO2, weak acid, titrated with strong base. Now I want to know what is the pH after adding 5 milliliters of KOH. So this one, I need a Bca table. So just like I did before. So Bca before change after. Everything has to be converted to moles before it can go into this table. And this one, we are going to not just use the H plus and the OH minus. We're actually going to leave it as HNO2 plus OH minus, and that's because it doesn't completely dissociate. Now the KOH, we can get rid of the K, because remember, if it's strong, that K is not going to have an effect. So that's why we can just use the OH minus, but for the HNO2, we have to leave it as is. So for that one, we're going to get then NO2 minus and H2O, because that H plus is going to react with the OH minus to give us H2O. Now, if you don't want to put the H2O in there, you don't have to, but just so we can see where that all goes, I'm going to put that there, and then I'm going to have to erase it in a minute because I'm going to run out of room here. Okay, so then before we can put these in, and I'm going to, like I said, I'm going to erase this just because I don't have any room here. Before I can put those in, I have to change everything to moles. So for the HNO2, I have, and I'm going to just, again, to save space, I'm going to convert these to liters before I put them in. So 0.04 liters, 0.1 mole per liter is 0.004 moles of HNO2. So this is similar to what I did on the last one. So again, anytime you're using Bca, has to change everything to moles. Then down here, 0.005 liters, that's my KOH. That's also, oh, I'm sorry, this is 0.2 moles per liter. So I'm putting in 0.001 moles of KOH. Okay, just like before, whichever one is smaller, that's the one that we're subtracting. So in this case, the OH minus is smaller, so I'm going to subtract that. Before I do that real quick, I'm going to go back up here. So the NO2 minus, we're going to assume is 0 to start with. But on this one, because it's weak, it does actually add a little bit of NO2 minus in solution. So this is why this calculation is going to be a little bit more complicated, because it's going to look more like a buffer problem. Okay, so then if I go back down here, this is going to be 0. 0.00, whoa, that's not the color I wanted. 0.003, and then 0.001 moles. Okay, just like before, I have to then divide by new volume. So that's what I'm using down here. So this is new volume. And to get the new volume by adding the volumes together. So I'm going to divide both of those by 0.045 liters. And then that gives me the molarity. Okay, so this one has a molarity of 0.07. This one has a molarity of 0.02. Okay, one more step. Any questions before we do the last step on this one?
Where'd you get the 0.045 liters from?
So that when you change this number down here back to molarity, molarity is going to be moles over liters. So to get the liters, you're going to go back to the problem and you're going to add the volumes that they gave you together. So since we mixed those two together, we had 40 milliliters of the weak acid and 5 milliliters of the strong base. So we added those two together. So that was 45 milliliters. So then all I did was converted that to liters. And then that's what I divided those by so that I could then get those back to molarity so that I can then use those to calculate the pH. Other questions before we do this last little step here? Okay, so then once you have your new molarities, we're going to go back and use that Henderson-Hasselbach equation. So I'm not going to test you over buffers on this test that we're doing here because we covered buffers a long time ago. But the one piece of this that you will need is that Henderson-Hasselbach. So Henderson-Hasselbach equation, you would have to know the Ka for HNO3, that would be given. So 4.5 times 10 to the negative fourth. And this was for HNO3, or I'm sorry, HNO2. So that would be given. And if you remember the Henderson-Hasselbach equation, it was pH equals pKa plus log base over acid. So when you have this weak acid, strong base titration, it's basically acting like a buffer. That's why you can use this buffer calculation. Now, if you don't want to use Henderson-Hasselbach, you could take these values and put them into an ice table, but this is definitely the quicker way to do this. So pKa, I'm going to take the negative log of the Ka, which gives me 3.34, plus log base. So my base, this is my conjugate base, which is NO2 minus, so 0.02. This is my acid, and this is going to be 0.07. So my pH, after I've added that KOH, is going to be 2.80. Okay, so those are a little more involved than the strong acid, strong base, but the Bca table is always going to be the same setup. You set up your equation. If it's strong and strong, it's just going to be H plus OH minus to H2O. If it's weak and strong, it's going to be the weak acid plus OH minus, gives you the conjugate base, plus water, and the water you don't have to include. Everything always has to be changed to moles first, whether it's strong or weak. You subtract the smaller of the two that you start with, so either the acid or the base, whichever one is smaller, that's what you subtract. And then when you get to the A, after you added or subtracted, you convert back to molarity. Then you take it into the Henderson-Hasselbach if it's weak and strong. If it's strong and strong, then you just use that final OH or H plus to calculate the pH. Okay, the last thing you could be asked is if it's weak and strong, you could be asked at the 1/2 equivalence point, what's the pH? So like we said a minute ago, by definition, pH equals, just a minute, let me make sure this is still recording here because I don't know if I have this, hope so. pH equals pKa. So the pH at the 1/2 equivalence point is 3.34. And that was that value that we used over there. So the only calculation you would have to do for that one is just find the pKa given the Ka value if you didn't have that already. Okay, what questions do you have about that one? Okay, and these, once you do a few of these, I have a practice sheet in there that goes through basically very similar to these example problems, and then your homework problems, again, are very similar to this. So by the time you get through a few of them, hopefully that'll make a little more sense. And then I have more practice. If you want to go through some more practice later in the week, we can definitely do that as well. Okay. All right, so then the last couple things, those are the only calculations you have to worry about. The last couple of things is just going over a couple more definitions of things. So these we're not going to do calculations on. So if you have a weak base and a strong acid, again, characteristics for this, the initial pH is not as high, the equivalence point is below 7, and then again, it's the more gradual curve. But like I said, we're going to focus on those first two types that we talked about. But this is the same version of strong and weak, but this is just weak base, strong acid. And then the other thing, just so that you've seen these before, we're not going to do calculations with polyprotic, but a polyprotic acid titration is going to have an equivalence point for every loss of an H that there is. So like this would be a diprotic acid, because there's an equivalence point for the first loss of an H, then there's an equivalence point of the second loss of an H. So for this one, instead of it just being one curve, it's going to have those little bumps in it depending on how many H's there are. So I'm not going to ask you questions about polyprotic acids, but again, just know that these, again, the people I'm most worried about are people that are going on to take this again. Polyprotic acid titration, the curve looks different because every time you lose an H, it has its own equivalence point. Last couple things to talk about today are indicators. So the indicators are pH dependent colors. So the endpoint is where the indicator changes color. So different indicators have different endpoints. And that tells you when there's an equivalence or when you've hit the equivalence point. So you're going to choose an indicator based on when that endpoint or predicted endpoint is, or predicted equivalence point is. So phenolphthalein is the one that they classically use for strong acid and weak acid titrations. So you can see that it changes somewhere in between 7 and 9. So it'll change just a little bit past 7, which is still why we use it for strong and strong. But then when you get to that really dark color, that's too far. That's why we stop it when it's just barely a light pink color. Here's your example of when you would want to stop that. So you can see that super light pink color. So when you start with this particular graph, if you look, this is an acid-base titration. So this one would have, this would be a weak acid. If you look at the initial starting point, so the starting point's between 2 and 3. So that would tell us we're starting with a weak acid and a strong base. You can also see that the equivalence point is above 7. So that's our second feature. And then you can see that gradual curve. If this was strong, you'd be starting somewhere down here and it would go up and over. Okay, so this would be strong acid, strong base, or this is weak acid, strong base. But this shows you, if you're doing that indicator, if you're doing that titration, which you hopefully saw in the video yesterday, that shows you what that color needs to look like. There's lots of different indicators. So if you're doing some of those weak base, strong acid titration, some of those other titrations that we looked at graphs for, then you might need to use a different indicator. So this is just an example of another indicator. This is methyl red. Methyl red tends to be kind of a reddish orange color. And you guys used this when you did the equilibrium lab. And then it goes to kind of a yellowish color when the pH gets higher. And then here's a chart of all kinds of different indicators. So you can see that the phenolphthalein changes up here, but there's lots of other indicators you could use. Some of them have just 2 color changes. Some of them have a range of color changes. So you're gonna pick the indicator based on where that predicted equivalence point is. Okay, that was a lot of new stuff. A little more complicated than the stuff we've done in the last chapter. Any questions, anything else you want to talk about today before you start working on some practice? Okay, so in your, I will post the recording of this, so if you need to watch this again, or if you need me to work out any of the other practice stuff that you have, if you just want to watch more examples, I'm happy to do that. In your post on Google Classroom, there's a practice sheet. One side is a strong acid, strong base. The other side is a weak acid, strong base. So you'll have examples of practice of going through the same thing we did in those examples. Homework problems are the same thing. They should follow the same pattern. Tomorrow we will meet and go through the rest of the notes, which is just one more section on solubility. Still some ice tables, but it's using a different type of K this time. Again, different, but pretty straightforward. So we'll do that tomorrow. And then Thursday and Friday, you'll have some time to catch up, review, and then kind of figure out what do you need more help with? Do we want to meet again on Friday to do some more practice stuff? And then, like I said, test on Monday. Well, it's just going to be basically 2 short answer problems. One of them over titrations, one of them over the KSP stuff. All right, any questions, anything else before we end the meeting today? Okay, let me know if you have questions while you're working through stuff today. For the lab that you did, you should be able to go back and do those last 2 questions. Those are just those solution stoichiometry problems. So if you need help with those, let me know and I'm happy to work those out for you or help you work those out. And if you don't have questions, I will see you guys tomorrow morning at 9:30 again.